So,
Can I go back
yeah.
real quick? Sorry. On the right hand side, you see your little window.
Yeah.
Where it says your name. Go up to that and go to those three little dots. The right hand corner of it. There you go. Oh, never mind. Just the dots. All right.
Yeah, no, it's good. Any idea would be helpful because sometimes it works, you know, and sometimes it doesn't. So,
Yeah, sorry.
and I asked the guys, I think that maybe the UCIT guy knows, I can ask him. But yeah, so what he says, I don't think is right, like my opinion, but you can have your own opinion. What you might take this side and say, yeah, he's right, and then just blow off the idea that the energies aren't right, you know. Like high energy is bad, so it's not going to have PN. So the other thing is and the other thing is what's the other thing? There's like this excluded, like the solvent will go into the structure, right? But basically it's under shear. So we have like the Stokes equation for the spheres to get the Rouse. So you have a spring and you have a Stokes, and that gives you a relaxation time from the whole thing. And that can give you the whole dynamics. But he doesn't have any Stokes law in his equation. He's just got the spring constant. And one's a Feeney spring constant. So it's got it, when it fully extends, it goes to infinite force. So, and then for this particles, it's a normal spring constant. So it could spring forever, but there's probably the spring, he doesn't give the coefficients that I could see, but there's probably the coefficient for these is huge. So it doesn't matter. So the polymer is a weaker one, it can actually stretch. So so that's a little bit different than Rouse. Rouse doesn't have a Feeney potential, it's got just a spring potential. And then the other thing is Rouse has the Stokes law, and he doesn't have that, but he has all this molecular dynamics. So the molecular dynamics takes the place of Stokes law. Like he's got a force, he adds up all the forces and all the energies in the system, and then figures out to minimize that. So he's gonna, so that effectively does Stokes law for you. And it gives you more detail, like every bead in there, how it's gonna move and what the overall impact on the energy is. So he's effectively the Stokes law, because the Stokes law is just for one chain, it's one isolated chain. And he's got the whole system with the particles and the polymer, and it's concentrated. It's not dilute, so it's worthwhile just thinking about. So this is a standard way to do these simulations. So it's this you'll see in every paper will have exactly the same thing, maybe slightly different. So anyway, it's good to compare the things. Like this, kind of the Stokes law is more or less replaced by this 612 potential partly, you know, it's summed over everything. So it kind of gives you the. So the other thing, Mike had some question about the first question. But I guess that's it, just to compare the two. That's the comparing the energies. Compare the structure with the coarse grain model. So he's basically using, like, it's similar, like the Rouse model is similar to what he's doing. And it's, you know, they're different, but they're similar. There's some similarities, you can compare them. And anything else on this? It's not that, you know, it's not particularly easy, but I think if you go through this, you can kind of figure out both how the simulations work and also how the Rouse model works, and how the things match together, and how he's got this prediction of this power -2 for the mode thing, and also it's all kind of, a lot of things are in there. It's not bad. It's like a kind of a simple paper compared to this. Like I spent a whole day looking at this sticky Rouse model thing. And it's like, yeah, it's got the Rouse model in it, and it's got the spectrum and everything. So it's got a lot in it. But I mean, man, this is like pretty complicated if you have to go through this. So it was too much, I think. Like he gets into graph theory and things. I still don't know exactly what graph theory is. You know, I mean, you can Google it. There's a wiki page on it, but that doesn't explain it. And then like all I've seen, you pick up a paper and it has something like this, and this is supposed to mean something. So I don't really get what this means. Like supposedly if you're doing tensors, it's got all the tensor information in this picture. That's the idea of it. You know, and then you can simplify. I think either in this or in the supplemental, he goes through like the graph theory to show how the different networks connect together. You know, how you can put that together. Maybe it's in, but again, like it seems to be too deep to. He's got a mapping that's just graph theory, and then he does this derivation. I spent a whole day looking at this thing, and then I just decided that it was like too much, you know. Plus, it's there. So this is supposed to explain all the math in the paper, like graph theory. So, but I mean, to figure out what this means, I don't know. I don't really know how to do that. You'll see this in papers once in a while, you know. So anyway, so that's off track, I guess. But anyway, so hopefully that's all right. There isn't, I mean, there's not necessarily a right and wrong answer. Just try to justify whatever you say. If you agree with what the guy says in the paper about that they're attractive, try to justify that somehow, you know, to say, look, yeah, that's true. So I kind of redid the slides. Let's see, on this thing, I wanted to go up to 48, I think. So let's see. So anyway, I redid these slides and I put a new set in that kind of followed what I did. It seems like all this stuff is disjointed in the notes, you know. So we already went through the Rouse. I don't have a drawing of the spring and beads on this, but this has the equations I went through in class. How this the del becomes small, so the sine squared becomes just the value. Then you have basically m squared coming out of this. Tau to the -1 goes with m squared. It also goes with nr squared. So tau is proportional to the molecular weight squared. And it's proportional to 1 over m squared, which is what he uses in the paper because he can't like easily vary nr. Because within, all right, so Rouse only works for short chains. Once they entangle, it doesn't work anymore. So your range of NR, and he's got 30. So if he goes to 100, they'll probably entangle. So then it'll fail. So he's kind of limited in molecular weight range. So looking at the molecular weight dependence in a simulation, it probably isn't going to cut it, you know, to demonstrate the Rouse behavior. You can do it experimentally. I mean, that's actually. Well, the plot of viscosity versus molecular weight, wherever that is, it shows that it's power 1. So because you have that the relaxation time goes with molecular weight to the power 2. So this del 1 over del, so it's 1 over tau is 1 over n squared. Because this del is such a small number because it's m, which is 123 over like 10,000. So that means sine squared equals sine of x equals x. So the tau goes with n squared, and then you have to do this concentration business. If you cut so when you put it, so this is for one molecule, but if you want to do shear, you have to have a plane that goes through space. Then how many molecules cut through that plane is going to go with 1 over n, because the concentration, it's a mass, it's a per number or something. So you end up with 1 over n. That divides out, and you end up with viscosity is going to go with n. Tau and viscosity are proportional, but when you go to a bulk system, you have to multiply by the concentration to get that plane cutting. That removes 1 power of n, so you end up with viscosity goes with power n for the Rouse. So that's the main prediction actually, and it's a prediction that you could have anticipated. Like if I have twice the molecular weight, it's going to have twice the viscosity. Like it's just like you have a train, you add on another car, that increases the force it takes to pull the train. So that's pretty obvious answer from a kind of complicated thing. So, and then anyway, the way the energy goes for these modes, most of the energy is in the first. 90% of the energy is in the first mode. Like where the string has 1 vibration in it. So you can forget about all the other modes and you just call that mode the Rouse mode. That's the Rouse relaxation time. And you use m equals 1. and you get that time here. And you also get the viscosity and the diffusion coefficient. And then with that, then the whole chain just becomes a dumbbell, what they call a dumbbell model. So it's got the bead with the Stokes law, and it's got a spring, which is the whole chain. So it's just a dumbbell model. And dumbbell model is pretty well known, and that's what this decay, and then so there's random fluctuations. The GT is a random fluctuation. That's got the friction factor times the velocity, and du dx is the spring constant term. So it's like force times distance is energy, so du dx is force. So that's the spring constant thing. And in Langevin, you divide by the friction factor, and this GT just becomes like a velocity, like an instantaneous velocity caused by temperature. Randomly, the things are moving around. So you have this pulsation going up and down where randomly, and then you have a decay back to the 0 point, the average position. So the Rouse becomes the same as a dumbbell. The only thing you really get out of that analysis is kind of a molecular weight dependence of the tau and of the viscosity, right? But the physics of how it behaves is exactly like a dumbbell, like a simplest possible dynamic system. Single relaxation time. So, and the relaxation times the viscosity divided by the modulus kind of thing. So it ends up being just the simplest thing. And let's see. So another prediction that I didn't like, let's see. That's the Rouse. All right, so there's some other, this is the other prediction that the modulus, and within the Rouse, the storage modulus goes with the frequency to the 1/2 power. I didn't derive that. It's not derived exactly in the book I have, but this is the common thing that you see. So you see two things. The storage modulus down here, when it's in the flow regime, has a power 1. So it's going up slowly. Let's see, power 2. It's going up rapidly, and then the end of this thing. Not that far here. So the storage is going up with power 2 of the frequency, and the loss is going up with the power 1. So there's a crossover where you get to the rubbery plateau. So neither of those is the Rouse 1/2, right? Because this is entangled, that's why you see a plateau. So it's not going to obey Rouse behavior. Anyway, this behavior is just general fluid behavior. This just means it's a fluid. So I'll show you, I can show you where that comes from, where this power comes from. So this is probably the most important powers, like 2 for the storage and 1 for the loss. And that's just comes directly from Newtonian behavior. It's like converting flow to modulus, to complex modulus. Then the Rouse shows up way out here where you're inside the reptation tube. So I'll talk about that later on, but basically within the tube, it goes to the Rouse prediction of 1/2. Right, see where you see the Rouse in a normal polymer dynamic viscosity or modulus plot that's done on a viscometer, then you see the Rouse way at the end here, which within the entanglement tubes. And out over here, you see just flow. So the flow part, so you have that in here. So see if there's a simple way to do this without going through all the rest of this. So this is the simple way. So, all right, so there's two things. So there's the compliance and the modulus. Okay, so the compliance is you put a force on the stuff and watch it like drip down slowly, right? So you have a fixed stress, then you have a strain increasing. So usually you have strain times modulus gives stress, and then you have stress, which is fixed, times the compliance gives you the strain. So the compliance is a function of time, and it's proportional to the way the thing is stretching out. The two things, all right, so you can get the same information from both, but it's easier to derive the compliance one because it's got to do with strain, because you're talking about flow, you have the strain rate, so change in strain with time, which is also the velocity gradient. So it's going to be y dt would be the velocity horizontally, and it changes in the x direction. So it's dy dt dx, or it could be strain, shear strain dy dx, and then how that changes with time. So it's either velocity gradient or rate of shear are the same thing, right? Just the order of differentiation difference. Right, so if you have the rate of strain, then that's going to follow this changing strain thing with the fixed stress. So compliance is the natural way to look at this thing, even though modulus is the way we usually look at the world, because you don't usually have a droopy thing in measuring. You usually have a fixed strain that you put it and watch the stress change with time, because the droopy thing never ends. It's an exponential decay, so it will go forever, whereas the modulus thing kind of ends more or less. So anyway, the compliance is easier to understand from a modeling perspective. So everything's done in compliance, and then converted to modulus. Okay, just maybe it's just to make things confusing. I don't know, but anyway, tau here's the stress, the shear stress, and this is the strain, and that's the compliance. And if you plot the compliance, if you do this droopy measurement, so at short times there's a J kind of constant. It's like the thing doesn't droop immediately, then it's going to find you have entanglements, and if you wait long enough, it'll just flow. So in the final flow region, if you have this thing, and then you just take the derivative with time, so what's the change in compliance with time, then that's going to be the same as the change in the strain with time. And that's, since the stress is fixed, that's going to give you the viscosity as the slope of this thing. So in the terminal flow region, this guy is just 1 over the viscosity. The slope is the viscosity for the compliance once you get to this terminal region. So if you want to just consider the terminal region, you have this kind of simple thing, and the slope's 1 over the plateau of viscosity. Like when we had viscosity versus shear rate, there's a plateau part at the low end, which is the long time, like 1 over frequency. So short frequency is long time. So the plateau part is just 0 shear viscosity, A to 0. Right. So anyway, so that and the compliance curve is a straight line. It becomes a straight line with time. You know, it's log, but that slope is 1, log plot. So then you have this at low frequency, you can write this complex compliance. So in terms of frequency, it's going to be 1 over the viscosity, and then times the frequency, because this isn't the derivative, right? So it's got the time in it still. It's like 1 over time. So if you do J and then T up here, so you have J is T over N0 plus a constant, then T is 1 over frequency. That's the lost part, so it's complex. The other part, the constant you got, is this storage compliance in the flow regime. So it's kind of like a transform of this thing into frequency. In fact, it's a Fourier transform of this into frequency domain. Gives you this equation, which is just an integral, and then E minus I omega t, and you can integrate it and get this. So anyway, this is the complex compliance, and the complex. So the complex compliance is 1 over the complex modulus. Okay, so this is showing the complex modulus, right? And the flow regime is down here. This is a storage modulus, right? So the storage is a real part of the complex. So you just take 1 over that. So 1 over that gives you like 1 over this thing. If you multiply everything by viscosity frequency, you have viscosity frequency times J0. It cancels here, you just get I. Then the top becomes the viscosity frequency. Then you want to separate this thing. So always, if you have a complex number here, you want to make it like the real part and then the imaginary part. So you have the storage modulus, storage compliance, or in this case, the storage modulus, because you 1 over, then the loss modulus here. Right? So you multiply it by the complex conjugate of this, which is the I part is negative. So you multiply the top and bottom. That means you end up with plus I times minus I, which gives you plus 1, because it would have been -1, but I squared is -1, so you have plus 1. Then this term gives you that thing squared. Then you have this thing times I and this thing times minus I, those cancel out. So that cleans up your whole system for the denominator. And the numerator has the real part and the imaginary part. You're all set. So all you do is multiply by the complex conjugate of the denominator on the top and bottom, and then you get the answer. That's how you do it for everything. Right? So here, like when you do that, you immediately get the frequency squared for the storage, and it's frequency to the power 1 for the loss within the flow region at the low frequency, because this is only good at the low frequency region, low time, right? So it's not that mysterious. It's just a matter of messing around with complex number, and you can just get that. And it has there's no model, there's no Rouse model or anything down here. It just assumed it was Newtonian fluid. So any Newtonian fluid should have this behavior. So any Newtonian fluid should have a storage modulus at low frequency. I mean, within the Newtonian regime, which is kind of strange. But it kind of makes sense. Like if you jump off a bridge into water, you splat on it as if it's concrete. Like that's why people die when they jump off bridges. So even water, which is the prototypical Newtonian fluid, acts like concrete if you hit it at the high enough frequency. Right? So there is a modulus to it, even though you don't think there is. And then the storage and the loss part is just the viscosity times the frequency. Right. So you can kind of break apart. So that's why it behaves that way. That's why you get this crossover. Right? So you get the crossover when the thing starts to look like a solid, and this whole thing falls apart. You don't use this anymore. Then it's just got a flat modulus at that point. Right? So yeah, so that's why in the flow part you get this power 2 for the G prime. Then you reach a point where you see a plateau where it's a rubber, because on the time scale the entanglements can't relax. You get rubber. Then you see Rouse behavior at the high end, at the high frequency where you look at within the entanglements, and the thing just flows there. I mean, it flows like a Rouse fluid. It's like a spring controlled viscous element thing. Then what is in here? So basically everything depends on 2 parameters. That's the idea. So you could have the plateau modulus, and then you can get the viscosity, zero shear viscosity from this part. And from those 2, you can get the whole thing. Right? Like here, the argument is a zero shear viscosity to the 1/2. So the main theme is that there's just 2 numbers you need to get every possible feature of the system. Like if you want to know the plateau viscosity, you have to integrate the time-dependent modulus. And you can also integrate, you can get this zero time compliance by integrating this thing times T. If you divide those 2, you get something that has units of time, which is called the viscoelastic relaxation time. So it's this compliance. So you're not used to working with compliance, but basically you need it to get this, looking at this thing. So it fits together with the compliance, to get the thing to make sense, I think is how it works. So it's that business. So that's part of this. So it's possible to kind of make sense of these things. Let's see. So I went through this. All right, then there's some other things that you'll see, like we'll definitely see in papers, right? There's the Cox-Mertz rule that the frequency is like, you can convert the time dependence to the frequency dependence. They're the same thing. In other words, it justifies that you can do a oscillatory viscometry measurement to get the plateau viscosity from it, things like that. But you'll see people say like Cox-Mertz rule just means that the oscillatory and the steady shear experiments are the same experiment. Then there's this business of the Kramer's Kronig relation. that relates, that's basically relating, what is it doing? It's relating the storage and the loss to each other. So Kramer's Crony, a lot of these things were developed for dielectrics, because so you have like a dielectric material between two plates. This, like, measure the impedance, you have to do an AC. Like, to get the features of it, you need an AC, and it's got to do with the relaxation time of the molecules. So they're polar, they're between a field, and they're going to orient and kind of oscillate back and forth. So it's like a vibration going on, right? So basically, to understand that system, you had to develop all this math. So basically, they're talking about the electrical susceptibility is this alpha. Alpha is the electrical susceptibility, but it could be just as easily the compliance, the oscillatory compliance, right? So basically, all the math, they'll switch back and forth between susceptibility and compliance, and then modulus. So everything kind of relates to each other. So the first thing is that if there's only two numbers that relate everything, that means you can relate the storage and loss together through this integral. So that, like, one is the integral of the other one. So in other words, there's a response function. Like, if you pulse the material and then look at how it responds, so say if it's mechanical, you pull on it, or you put a weight on it, and then you watch how it stretches after. So that's this time, this response function for material, and that's going to have an imaginary part to it, depending on if you in an oscillatory measurement, because part of it will be in phase with what's going on, and part will be like out of phase. So basically, you can calculate the in phase and out of phase parts by doing integrals of the response function. Right. So the two things, the storage and the loss, are related because they both relate back to that parent response function of the thing. But to get that relationship, you need to use this Cauchy integral, because you have to integrate a function that's like 1 over the frequency difference through 0. So that goes to infinity at 0. And it goes plus and minus on the two sides. So you have this divergence. It goes down and then it goes up. I mean, it comes down from infinity and it goes down to infinity at 0. So the 0 point can't be reached. So you need to use this Cauchy integral P to do that. And it just says, like, you're going to go almost to 0, some infinitely small step away from 0. And then you can do this integral and you do that integral, then add them. As long as that number is pretty small, then that gives you the answer. It's kind of an approximation. Right, so it's a way to do an integral when you go through something that would be infinity. This Cauchy integral, you need to do that to get this Kramer's Crony relationship between the two, between the loss, like this, the storage is the loss, so it's the same integral. Right? Storage is the loss. You have to integrate through all from minus infinity to infinity, which ends up being integral minus infinity to 0, but not quite 0, and then not quite 0 to infinity. Then you can relate these things. So the things are coupled together, like they aren't independent of each other. Right. So that's what this. So people just mention the Kramer's Crony. It means you only have to measure one of these. You can get the other from it. It's possible to get it if you can get the data to infinity, from both ends of infinity. I'm mentioning this because you'll see it just. You'll see the Cox-Mertz rule. They'll just say it. They'll just say the Kramer's Crony relation. They'll just say it. And they mean that the storage and loss are related to each other, functionally related. We got that already. All right. So this goes through. This is kind of a rewrite of the things. So we have the case. I already went through flow, right? And then there's something called the relaxation, which is like, basically comes from this dipole thing. Like, you have a dipole and then you have two plates, and there's an oscillatory field going on it. And then the dipole is flipping back and forth, right? And it's got like a viscous part that's slowing it down. It's got kind of a springing back because of the potential that's on it. So it's kind of got a relaxation time. It's going to have a relaxation time. So you say, if you want to talk about that in terms of compliance, originally this would be alpha, so I just put in J, but J is the way you do it for mechanics. You say it's got this relaxation behavior. This is just an exponential decay behavior. And there's also like a prefactor to this. It's going to be like JU unrelaxed and then plus this thing. But just considering the JU is 0, you can write this thing, right? And if you want to know, this is in a time-dependent measurement. If you want to know the frequency dependent, then you do a Fourier transform. So this is a Fourier transform is take the function, which is that thing. So here it's oscillatory, so it goes from, so you're oscillating from a compliance at the bottom and at the top in a sine wave. So that's the delta, is like the breadth of the oscillation of this thing. Then it's got this function as a relaxation. Then you multiply it by this complex sine wave. So it's going to be sine minus I cosine of omega t. So that's called a Fourier transform. It's like breaking apart this time dependence into a series of sine waves. Like these are sine waves. You're going to have different wavelengths depending on what t is. You're going to integrate for all t from 0 to infinity, assuming that you can start at 0 where there's no stress in the material. So there's a point at 0 where there's no stress. You're going to integrate until infinity over time. That would give you the frequency dependence of the thing. So this is breaking it into frequency 1. So sine wave that's like a micron in length or something, right? Or micron in wavelength, or I mean that's going to be in time. So it'd be like a second in time, and then one at 10 seconds, and then one at 100 seconds. So you can break apart this response into those sine waves, right? So you're integrating over all time, and you're using one frequency you get now, like one hertz, say, and then 0.1 hertz, and whatever other hertz you want, right? So you're gonna for each hertz, you're gonna have to go through an integral over time, and that'll give you the amplitudes of the response at different wavelengths, at different frequencies, time frequencies. So it's converting from this time decay to a frequency response, which should show features of the behavior of the material. Right? So anyway, the reason I'm going through this is because you're going to definitely see this, like this equation. So you'll see like that the storage and the loss of these weird ratios. You'll see this 1 over 1 plus tau squared omega squared, then whatever 1 plus tau squared omega squared. So like, where did that come from? So it's coming from this. If you do this integral, you end up, so this is just a simple integral, because if you have exponential times exponential, you just sum the arguments, right? 1 over tau omega, the prefactor is the same t. So you have e to the minus t times a constant dt, right? And then you have to convert, like this d of this argument would be 1 over dt, would be this argument dt, right? So you have to divide by that argument, 1 over t plus I omega, and then the integral of exponential is exponential. So you have delta j, well, the integral of exponential is exponential, but exponential of 0 is 1. Exponential of negative infinity is 0. So you're going to have 0 minus 1 comes out with this thing. The minus is missing, but basically, the minus came from this minus. So the minus is plus. So you end up with delta j, limiting this exponential gives you just 1. And then you had to divide from that in order to change it. It's like y is this and x is this. And it's got to be divided out in the integral, right? So that thing just comes out. Then you just do the cleanup to get the real and imaginary from that. So you multiply by 1 over tau minus, and so the complex conjugate of that, right? And then that'll give you this thing, 1 plus tau squared omega squared. If you multiply through by tau, and then it gives you the real and the imaginary parts. Right? So you can say that if you have this relaxation, it's going to result in this kind of complicated looking function for the storage and the loss. Right. So again, the reason I'm saying this is that you'll see someone will just spit this out and say, like, where did that come from? And what are they talking about? And what it has to do is just have one relaxation time. So the simplest possible system, you just have one relaxation time. And that time is going to be the viscosity over the modulus. And then that looks like this in a dynamic experiment. Even this looks pretty complicated. That looks pretty simple, relatively simple. So this is the same thing, right? It's just you're going from a time-dependent measurement to its frequency-dependent. In fact, in that paper, they show that, for instance, like in that, where that paper went, somewhere in this paper, not this paper, in this paper, they say that, not in the supplemental, but in the actual paper. Somewhere in here, they'll just flip out that equation, and then you're supposed to know that that's what that means, you know. It can look pretty mysterious unless you kind of figure out that's his time dependence. Pretty sure it's in here somewhere, maybe not. He just gives that exponential time dependence. Somewhere in here, he gives that frequency dependence function, but anyway, it doesn't matter. So anyway, that's a kind of an important point. Oh, and then how do those two things behave? Well, if it's a simple relaxation, this is how the compliance looks with frequency, and this is how the loss part looks. So it kind of looks like a, so if you take loss over storage, that gives you tan delta with phase shift of the response. It's like tangent of the, so you have the input wave and you shifted the response over by del. So tangent of that del is going to be this guy divided by that guy. It's like sine over cosine. So basically the ratio of these two gives a peak. That's what you see at the glass transition. When you look at the glass transition, you're looking for tan delta versus frequency, you see a peak. And the peak is the glass transition. So that means if it was a perfect peak, that would mean that the glass transition was a simple Debye relaxer with a single relaxation time. It's actually more complicated than that, right? Because it's going to have more than one relaxation time. But anyway, so that's another thing, right? So all this stuff doesn't have to do with flow at all. Like flow is a completely different thing. This has to do with some kind of a relaxation. It's got a relaxation time, and flow doesn't. Flow is just its viscosity of the stuff flowing. Right, so you go in at the low frequency end, you just see flow. So you see this frequency power 2, frequency power 1. Then you get to the crossover, and that's like this viscoelastic relaxation time, this tau bar, the J0 times the plateau viscosity. Right. So, and at that point you see this. So you're transforming from, this doesn't work with viscoelastic flow. So you can't get the power 2 and 1 from this equation, even though it looks like you might be able to. This is only talking about a transition. And the other part is just talking about flow. So it's kind of a problem with viscosity, because you see in the spectrum, I mean, if you look at that viscosity curve with the time shifting, you know, if you convert it to size of things, at the low frequency end, the size that relates to that is meters, you know, and at the high frequency end, the size that relates to it is angstroms, right? So it's really like literally 8 orders of magnitude of size across that simple thing where you're just doing a vibration of a thing. So it's kind of amazing that you can get that, you know, from such a simple machine. Like it's not a huge electron microscope, you know, we're actually probing all these sizes with it. Kind of probing it, you know, but each part, there isn't like a universal interpretation to that curve. It's a piecewise interpretation. So you take, there's a flow part, there's this relaxation part, then there's the rouse part. So they're separate. You know, they aren't, it's not one function that fits the whole thing. Right? So it's kind of disappointing in that sense. People tried to, I mean, you can hack it and get a full fit to the curve, but basically there isn't a single function that like rules the whole thing. Okay, if you do have this, so then the other thing you'll see is if you do have this, and again, this is both in dielectrics. So if you're looking at batteries, you know, it's all dielectric spectroscopy. Yeah.
Question. So I know in asphalt, at least, a lot of what we would do instead of taking oscillatory shear measurements across the whole range of frequencies is that we would utilize time temperature superposition.
Yeah.
So we would do, I mean, you can do a frequency sweep to generate a master curve, but we would also do temperature sweeps. Is that common in other facets of polymer as well?
Yeah.
Okay.
Yeah. So you do, I mean, like usually what you do is you do a frequency sweep over like a decade and a half. Then you just ramp the temperature.
Okay.
And then you do just shift the things to match up.
Okay. I knew that's what we did in asphalt, but I didn't know if that was universal or not.
Yeah. So the time temperature works great, pretty good for the frequencies part of it. But you also have to shift the modulus part too. And that part is just witchcraft.
Yep.
So and people, it's funny, you read papers and everybody understands that that is just made up, you know.
Yep.
But anyway, it's funny to read how people try to justify it. But it's fine to do it. I mean, I think it's just how it's done. But basically, partly it's not the whole thing. Like the asphalt isn't all time temperature superposition. There's like stuff in it too, gunk and things.
Right.
So basically, that could be part of it. You know? But there's a lot of things that could be part of it. But nobody really knows why you have to shift the other axis. So anyway. Yeah, so everybody does that. That's the same in everything.
Thanks.
It's pretty funny that it's the same thing, you know, because you would think it would be different, but it isn't. Like it's the same. And it's probably the same problem that people have. Okay, once you have this curve, and if it's a single relaxation, then you can plot J double prime versus J prime in a cold plot, which is a nice thing because it looks simple. So basically, you can rewrite this complex equation into the equation of a circle. Well, this is the equation for a circle equals this. This is like the radius of the circle, right? So you have like the x, y is the prime, double prime, and x is the prime. So this is a dielectric measurement. The same thing you can do with compliance, and you can do the same thing with modulus. Right? You just plot double prime versus prime. Then you're looking for semicircles. Right? The radius is going to be the amount of this. So these are all, each point has a frequency and a temperature, but there's no frequency and temperature in this plot. That kind of fell out of this. Once you drew this up, and if you work through this, the math of this thing, the frequency drops out of it, as does the temperature. Right, so you just end up with a plot of double prime versus prime, and kind of get this radius of the thing. Right, and then the central position of it is this shift factor, this initial compliance in this case, plus delta J. So delta J is giving you the radius, and then like this shift factor shifts it from going from delta J, and then it'll shift over a little bit according to what your initial compliance for the thing was. Like wherever that plot was, it had initial flat compliance. So, I mean, there's various ways that you don't see this. I mean, generally at this end, so this is the high modulus end. So this is kind of the high frequency end of it, and the low frequency is kind of over here. So at the high frequency end, you know that the thing starts to have weird things happening. Like if it, say, it forms a network, then the network shows up here. And if it's a network, this Winter, who's a Winter and a guy in Germany, I guess is the name of it, but basically the loss and the storage become proportional to each other in frequency when you have a network. So you expect to see like a straight line coming off this. It doesn't show it in this data, but so you get to high frequency and then it'll shoot off like that straight up. And that means you have a network, right? So the circle means you have a Debye relaxer. These two cases, he's showing that one is just a dipole, like some molecule that's got a charge in each end, and it's a rod, and how it relaxes, and it's a perfect Debye relaxer. Then he sticks those rod things onto a PDMS as a side chain. Then he looks at the relaxation of that, and PDMS doesn't have a dipole, but the side group does. Then the relaxation shifted a little bit, and you can explain that with this stuff. But people do that. People mess around with cold plots quite a bit. Usually, you're just trying to show that you have a relaxation time. Like if it shows a semicircle, it means there's a tau associated with that thing. And it's acting like a simple relaxer. And if it deviates at the high frequency end, that means that it's forming like a network. If this is proportional to that, it goes off with a straight line. So the cold is another thing that people are getting from this stuff. There's a lot. I mean, there's a lot to it, but these are actually the highlights, you know. Like there's a lot to this, but basically, don't let this thing scare you off. Like people would just throw this out and like, oh yeah, of course. But this thing you might be more comfortable with. And just if you can look at that and think this, they're the same thing, you know. So, and then actually this thing and this behavior, like a glass transition, and this behavior are all the same thing. It's just an exponential decay with a single relaxation time. Right. So it looks pretty messy when you put in the complex numbers and all, but basically it's just a simple thing. It's a thing that's just like drooping down, and it's just like going exponentially down as it droops out, you know. So it's kind of the simplest kind of goo equation. This is the parent goo. Everything is goo, follows this law, you know. So and that means there's a lot of things that are goo, because you'll see this stuff all over the place, like both of those things. And again, like, so if you're looking at batteries, see, in dielectrics, you can relate it to the impedance, so you can relate in the resistance, right? So you can take these plots and get back the electric circuit that it came from. So if you have paint and it rusts, like you have a piece of metal, you paint it, you want to know, like, are there holes in it? So you can pick out from these dynamic dielectric measurements, like what the resistance is of the coating, how much does it store of the charge on the two sides, and then how much leakage is, how the mode of it breaking apart. Same thing with rust. You can study rust occurring, the chemical reaction with these same kind of plots. So it's kind of universal, like it's so universal, this stuff. I mean, you can apply it to dynamic for asphalt, for polymers, you know, for human skin or whatever. So anyway, so that said, what else is in here? This is, what is this? So it's possible to get, so if you have this complex compliance, then you want the complex modulus, just take 1 over. And then if you do the math for that, you can get the same equation. Like, in other words, you have an initial modulus, unrelaxed modulus, and then you have the same equation, but the tau is different. Okay, so the tau here is smaller than the tau here. And the taus are related by this. The tau for the modulus is like the unrelaxed over the relaxed compliance times the tau for the compliance. Right, so you get the same functional behavior. So you get these same plots. So you can get the cold plot, you can get the same thing, but this peak will be in a different position, because that times that is, this should be omega times tau in that t here. So this one would be in a different frequency, depending on if you use compliance or modulus, because of that thing. Then that gives you the thing I showed you before. That you can get this. You can get this universal this viscoelastic relaxation that relates it to time by this wherever that went. it's gonna be this, the viscosity times that J E naught. So you have the viscous thing, which is the storage modulus times frequency. And then this thing is actually G double prime, and that thing's from the, this thing is from the compliance part. So the coupling of the plateau modulus and this compliance zero gives you this average viscoelastic relaxation time, this thing, T tau bar. So so I guess I'll go through this maybe a little bit more next time. We're out of time for it, but it's complicated, but it's part is like pretty much in every paper dynamics.
Do most papers use like a real simple model, or do they include like, so this is like just one kind of,
One relaxation.
yeah.
Yeah, so you integrate them. So the Boltzmann principle is you can break it into one relaxation.
Okay.
So you integrate it. But generally, the simpler, like if you can use one, if you do a cold plot and you see a hump, you say it's
Yeah,
one
it's good enough,
relaxation.
I'll just use the one.
Yeah, it's good enough because anything more is going to be so complicated. It's already complicated. Anything more is just going to make it
Kind of
worse.
like, oh, what is it? The second bureau coefficient, what do you need the third and fourth?
Right.
bit?
Yeah.
Like not really.
Yeah, you don't need
Good.
it because you're not going to get any more understanding. The question is, are you getting more understanding by doing that? You know, why are you doing it is the question. You know? Like,
Yeah, if you just want an understanding, then you don't really need it. If you want actual
yeah.
numbers made.
if you're doing it for fun of just doing math, you're going to drive yourself nuts. You know, but realistically, like it's only going to be, you got the answer already generally, and that's